Hi everyone, I am Dr. Upendra, Assistant Professor in Chemistry, Government Degree College, HAYATHNAGAR, Rangared District. Today we are going to discuss about pericyclic reactions. These are concerted type reactions, so very important in the examination point. So and also CSIR gate exam also very important, IIT JAM. So now we are going to discuss about pericyclic reactions. So the next slide, pericyclic. So peri means before or around the reaction. The single step reactions which involves bond breaking and bond making process simultaneously takes place are called concerted reactions. No intermediate formation takes place in these reactions. Only cyclic state will formed and then product will produced. So cyclic state or transition state happened in the middle, so we get product or gives product. So for example, uh, Diels-Alder reaction. Diels-Alder reaction. So 1,3-butadiene, you take 1,3-butadiene and ethylene diene. So in the presence of light or thermal, we get this type of transition state. So pi electrons circulated as as around system pi system. This is the product cyclohexene. Here no carbocation, no carbanion, no carbenes, no intermediate, just bond bond breaking and bond making takes place in the transition state. So before we get product, one transition state we get. So this is the pericyclic reactions, concerted type reactions or single step reactions or atom economy reactions. Atom economy reactions. So consider these are stereospecific reactions. So specificity more in the concerted reactions. So here no reagents need, solvents, catalysts or any mediator no need, just thermal condition, that means heat or light need in these reactions. So photolysis or thermolysis only need. So how do you form product? We check here. So first of all, molecular orbitals. Already, as you know, atomic orbitals S and P, D, F, S orbital, P, D, F. These are atomic orbitals. EO. These atomic orbitals combine to get molecular orbitals. That is LCAO combination. Linear combination of atomic orbitals. So LCAO combination of atomic orbitals produces molecular orbitals. The number of molecular orbitals are equal to number of carbon atoms in the reactant. So for example, ethylene molecule, you take ethylene molecule CH2 double one CH2 ethylene molecule. Here two carbons is there, two atoms is there. So we get here two atomic orbitals produce two molecular orbitals. These molecular orbitals indicates with psi letter psi 2 is there, psi 1 and psi 2. These are molecular orbitals. So these are two types of molecular orbitals in the reactant molecules. So those are homo molecular orbital, LUMO molecular orbital. Homo means highest occupied molecular orbital homo. LUMO means lowest unoccupied molecular orbital. So psi 1 and psi 2, how do you arrangement of electron, that is electron configuration of pi system. So you Here one pi bond is there between two carbons. So one pi bond is equal to 2 pi electrons to pi electrons. Each molecular orbital consists of 2 electrons. So psi 1 2 electron, psi 1 2 electron, remaining molecular orbital psi 2 0, psi 2 0. Here highest occupied orbital, here only one is there, highest occupied molecular orbital, that is psi 1. Psi 1 is also called HOMO orbital, highest occupied energy molecular orbital. So if you take 1,3 butadiene, here 4 carbons is there, 4 carbons is there, 4 molecular orbitals we is there. You have psi 1, psi 2, psi 3, psi 4. So 4 molecular orbital produced in the system. So how many pi bonds is there in 1,3 butadiene? Here 1 pi bond, 2 pi bonds. 2 pi bonds is equal to 4 pi electrons, 4 pi electrons. So each molecular orbital consists of 2 electrons. So psi 1 2, psi 2 2, psi 2 2, psi 3 0, psi 4 0. Due to 2 pi bonds is there, 2 pi bonds is equal to 2, 2 plus 2, 4 pi electrons. Each orbital has 2 electrons. So psi 1 2, psi 2 2, psi 3 0, psi 4 0. Psi 1 and psi 2 occupied molecular orbital. Remaining two orbitals are unoccupied molecular orbitals. So here highest energy orbital is psi 2, due to number of nodes is there, more energy orbital. Nodes increases, energy of molecular orbital increases. Here psi 1, psi 2, psi 3, psi 4. So psi 1, psi 2 occupied orbital. Here psi 2 has one node, psi 1 no nodes. So nodes increases, energy increases. Highest energy orbital, it is an occupied orbital. So highest occupied molecular orbital here psi 2 orbital. So LUMO is lowest unoccupied molecular orbital. So lowest unoccupied molecular orbital here psi 3, psi 3. So psi 3 is the LUMO, psi 3 is the LUMO. This is HOMO LUMO orbital, HOMO LUMO orbital. So one more, LUMO means lowest unoccupied molecular orbital. The unoccupied molecular orbital with lowest energy is known as LUMO. So unoccupied molecular orbital with less energy, so that is LUMO. Here already we have discussed just now, psi 3 is the LUMO, psi 3 is the LUMO. For example, psi C double bond C single bond, C double bond C single bond, C double bond C. 135 try triene. So here 6 carbon atoms is there, 6 molecular orbitals, those orbitals are psi 1, psi 2, psi 3, psi 4, psi 6, psi 5, psi 6. So here how many pi bonds is there in the conjugated pi system? 1 2 3. 3 pi bonds is equal to 6 electrons. Each orbital carries only 2 electrons, 2 electrons, 2 electrons. So occupied orbital, this set, this is the unoccupied molecular orbital set. Here in occupied set, psi 3 is the highest energy orbital. How do you say this is the highest energy orbital? Psi 3 has 2 nodes. So higher nodes orbital has higher energy. This occupied molecular orbital has higher energy, that is HOMO orbital. So highest occupied orbital with high energy, HOMO orbital. Here psi 3, psi 4, psi 5, psi 6, LUMO set, that is lowest empty set. Unoccupied set, lowest energy is psi 4. This is the psi 4 is the LUMO orbital, psi 4 is the LUMO orbital. This is HOMO LUMO. Both orbitals, HOMO and LUMO orbitals are called, HOMO and LUMO orbitals are called frontier molecular orbitals, FMOs. Frontier molecular orbitals, HOMO, LUMO are called FMOs. So next, FMOs are involved in the formation of bond and breaking of bond, covalent bonds. So FMOs are involved in the transition state, transition state. So these are the participated orbitals in the reaction mechanism or transition state. So we get product from these interaction of orbitals. So next slide. So how do you designate the molecular orbitals here? So here designation of molecular orbitals, this is amplitude or lobe. Upper lobe indicates positive charge, lower lobe indicates negative charge. So don't confuse with positive means deficient of electron, don't confuse. So amplitude displacement of electrons in the upward direction, that is positive direction, or thick, here orbital lobe thick, here empty lobe, here thick lobe. That means indicates amplitude of electron density displacement towards upward direction, towards downward direction. Don't confuse empty orbital or more electron density. So here you take ethene molecule. In ethene there are two carbon atoms, so we take two molecular orbitals, psi1 and psi2. Each one contains two atomic orbitals. Psi1 and psi2. So psi1 indicates psi1 means no node. So psi2 means one node. So node is equal to n minus 1 nodes. So node is equal to n minus 1 formula. So properties here, symmetric properties. So two symmetric properties are considered in pericyclic reactions. Those properties are plane of symmetry or mirror plane of symmetry, that is sigma or m, axis of symmetry, that is Cn or C2 axis. In pericyclic reactions we have taken these two symmetry elements, so sigma and C2. So electron configuration, psi1 psi2 ethene. So psi1 M symmetric, C2 anti-symmetric, M anti-symmetric, C2 symmetric. So here with respect to symmetry element present, that is symmetric orbital, vice versa anti-symmetric or asymmetric orbital, psi1 to psi2 0 ground state configuration. This is psi1 2 orbital, psi2 0 orbital. Psi1 is the HOMO here, excited state in photolytic condition, excited state happened. So psi2 is the HOMO. So next one, what is the 1,3-butadiene symmetric properties. So this is symmetry properties. Generally two symmetric properties are considered. One is the M, second one is the C2. So an imaginary, what is the M, what is the sigma? An imaginary plane which bisect the molecule into two equal halves, then the molecule is said to be possess mirror plane of symmetry. When any imaginary axis plane cut the molecule into two equal halves, those two halves are mirror images each other, the molecule possess plane of symmetry. Here you take example here, psi1. So cut the molecule two equal halves, those are mirror images. So plane of symmetry present in the molecule, that is symmetric with respect to sigma. Automatically with respect to C2 in this anti-symmetric, C2 is absent. When C2 is absent, that is asymmetric or anti-symmetric. So in case of psi2, means how do you prepare psi2? For example, two lobes you take, this is psi2. For example, this one plus, this is minus you take. So psi2 means one node wants here plus upward direction, here plus downward direction. So that's why here node will get. Here minus downward direction, here minus upward direction. Node will present in this type. So we take this side to, this is the side to diagram. Side to no sigma, no sigma. So with respect to sigma, anti-symmetric or asymmetric. In the case of C2 sense, C2, so we get C2 is there, imaginary axis. So rotate 180 degrees around imaginary axis. So we get starting orbital. That's why C2 is present. C2 is 180 degrees. This lobe comes this lobe comes here, bottom comes top. So C2 present. With respect to C2, this is a symmetric molecular orbital. Symmetric molecular orbital. So molecular orbitals which are symmetric with respect to C2, then asymmetric, anti-symmetric with respect to sigma. So vice versa. Vice versa. So here for psi n molecular orbital, n is odd number, psi 1, psi 3, psi 5, psi 7 and so on. Then such orbitals are symmetric with respect to sigma. So odd number of molecular orbitals as sigma, so those are symmetric with respect to sigma, anti-symmetric with respect to C2. If n is equal to even number of molecular orbitals, those orbitals have C2 axis. So with respect to C2 and with respect to C2, symmetric orbitals. So controverse, that is reverse, anti-symmetric with respect to sigma. So if sigma is present symmetric, if C2 is present symmetric, so opposite to the other element. Next, here 1,3-beta diene takes example. So always indicates low to higher level energy indication side. So upward direction is the energy increases. Here psi 1, psi 2, psi 3, psi 4 and so on, energy increases. So top level has higher nodes. So here no, first one node after sigma, next C2. This is the psi 1 diagram. Psi 1 indicates no nodes, 0. So 0 nodes is the plane of symmetry present. So automatically C2 axis absent. So this is the C2 here. C2 is the absent. So here one node is there, one C2 side 2 is equal to one node is there, one node. So odd number of node, plane of symmetry absent. So automatically C2 axis present in the molecule. One is absent, other one is present. One is present, other one is absent. This is the vice versa process. Next one, psi 3, you get easily how many nodes is there. So 3 minus 1 is equal to 2 nodes. So 2 nodes are there, even number of nodes. When even number of nodes present in the system, so we get plane of symmetry. See, plane of symmetry sigma is present. So and then automatically C2 axis absent. So symmetric means plane of symmetry present, absent means plane of symmetry absent, or C2 absent. So next one, psi 4, 3 nodes, odd number of nodes. So sigma absent, automatically C2 present in the molecule, in the molecular orbital. This is the symmetry elements in pericyclic reactions. For example, next one, this is 1,3-beta diene. Here allyl radical. So 3 carbons are there in allyl, 3 atomic orbitals are there. So 3 molecular orbitals we get, those are psi1, psi2, psi3. Psi1, psi2, psi3. So allyl radical 3 electrons are there. 3 electrons. One is the pi electron, other one is the one single electron, unpaired electron. 3, sorry. So psi1, psi2, psi3. Psi1 has no nodes. Psi2 is one node is there. This is one node, maybe one node. Psi3 is the two nodes. Here one node, here one node. Psi3. So you have to here develop symmetry elements also. So when sigma is present, C2 is when sigma is present, C2 automatically absent. This is the electron configuration. So if you take HOMO level at ground state, Psi2 is the HOMO. If you take excited state, Psi3 is the HOMO level. Psi3 is the HOMO orbital. So next one, this is already discussed. So what is the stereospecificity in pericyclic reactions? Pericyclic reaction. So which product produced in thermal condition or photochemical conditions? So generally pericyclic reactions are initiated by heat or light. So heat indicates already heat indicates delta, light indicates H nu. So in the presence of delta, thermolysis; in the presence of H nu, photolysis. Or these reactions are highly stereospecific. That means thermal and photochemical process yields products with different stereochemistry. That means in any pericyclic reactions, same product is not obtained both in thermal and photolytic conditions. Not same product produced in the thermal condition and photolytic conditions. And that means different product will be produced in different conditions in pericyclic reactions in thermal and photochemical conditions. For example, a reactant with 4 and pi electrons forms cyclic product in light conditions which did not form in thermal conditions. This is due to different orbitals are participated in chemical, thermal and photochemical conditions. This is the main reason FMO, frontier molecular orbitals. Frontier molecular orbitals selected from ground state only at thermal conditions. But in photolytic conditions, HOMO-LUMO orbitals, those are frontier molecular orbitals, selected from excited state in photolytic conditions. Excited state in photolytic conditions. That's why product will be changed. So here 4 and pi system 1,3 beta diene substituted 1,3 beta diene. So 4 and pi system in thermal condition cis product will get thermal condition. So in the same reactant condition is different. Here photolytic condition we get trans product. Here cis stereospecificity, here trans stereospecificity is there. Those are different products in different conditions. That is the stereospecificity of pericyclic reactions. Here same 1,3,1,3,5 hexatriene also. This is 4n plus 2 system, 4n plus 2 5 system. Thermal conditions we get cis product. In the presence of HNO photolytic condition we get trans product. So it is the stereospecificity of the reaction. What happened in the mechanism we have to observe in this chapter. So how do you get cis and trans product in different conditions? So we have to check how many types of pericyclic reactions present in the reaction mechanism also we have to check here. So next slide. Types of pericyclic reactions. The three important types of pericyclic reactions are there: electrocyclic reactions, cycloaddition reactions, sigmatropic reactions. So electrocyclic reactions, first one, A concerted reaction in which the new sigma bond is formed at two terminals of a conjugated pi system, resulting to form a cyclic product is known as electrocyclic reaction. That means in electrocyclic reactions, expensive of two pi bonds, there are one new sigma bond, one new pi bond are formed. So two pi bonds consumed and then produce one new pi bond and new sigma bond, one new pi bond in the middle, one new sigma bond at terminal. So you have to take 1,3 butadiene is the best example, that is 4 and pi system, 4 pi electrons is there. So delta or h nu take dual, these are dual reactions or forward reaction, backward reaction takes place. So in the presence of light or photolytic condition, we get cyclobutene. Here four carbons. This pi bond comes between CH and then one new sigma bond formed at CH2. So this is the new sigma bond. This is the new pi bond. Simply you can say one pi bond is lost, one sigma bond you get. This is the electrocyclic reaction. Or you can write concerted mechanism also. So 1,3 CH2 you can write like this also. C CH2 middle one, this is sigma bond. So electrons are transferred one place to other place. So cyclic transition state, this is cyclic transition state or transition state. From this we get the product. So in this reaction, one pi bond is consumed by the molecule and one new sigma bond produced in the product. So if you take 4n plus 2 pi system, 135 hexatriene, so you get cyclic product, cyclohexadiene. This is the electrocyclic reaction. Here also you can write cyclic transition state. So cyclic transition state, that is the concerted mechanism, concerted reaction. So electrocyclic reactions, one molecule participated in this reaction. This is one molecule to one molecule produced. But cycloaddition reaction, two molecules participated in the reaction, you get only one product. So but concerted mechanism, single step mechanism, these are stereospecific reactions, more predominantly form only one product only. So more stereospecificity is there. So these reactions are very, very important. So next one, cycloaddition reaction. Cycloaddition reactions again classified into two types. So first, electrocyclic reactions we have to observe. FMO approach, according to frontier molecular orbital approach, to predict the reaction mechanism or to predict the condition of electrocyclic reactions, one has to consider only HOMO level of the conjugated pi system. So here two rules is there. To predict the thermal condition, select HOMO level of conjugated pi system from ground state. To predict photochemical conditions, select HOMO level from ground state, excited state. So thermal condition, if you want to thermal condition, select HOMO level of conjugated pi system from ground state. In photolytic condition, select HOMO level at excited state. Do all possible rotations, those are con rotation and dis rotation. So con rotation means rotation around two double bonds in the same direction, either in clockwise or anti-clockwise. So both terminals rotate at same direction, though that is con rotation. Con rotation means same side rotation, either clockwise rotation or anti-clockwise rotation. So next one, rotation about two terminals in opposite direction. Opposite direction. One is clockwise direction, other one is anti-clockwise direction. So clockwise or anti-clockwise, that is opposite direction. So opposite direction is called disrotation. So when rotation results bonding interaction, then the process is called allowed process. If it is anti-bonding interaction, the process is called forbidden process, forbidden, that is anti-bonding, not allowing. So both lobes interaction, different lobes interacted, same lobes interacted, that is bonding. So here you can see here same lobes interaction, that is bonding takes place. Here opposite lobe interaction, anti-bonding takes place. So all possible rotations you do, and then if you predict the thermal condition, HOMO level select from ground state. If you predict the photolytic condition, you HOMO level select from excited state. This is the very important conditions in fmo theory. So first we need to examine thermal conditions for electrocyclic reaction. So you take 1,3-beta-die con rotation or disrotation. For example, first ground state electron configuration. So 4 carbons is there, 4 molecular orbitals, I1, Psi2, Psi3, Psi4. So in this 2 pi bonds is there, 4 pi electrons, Psi1 2, Psi2 2, Psi3 0, Psi4 0. So Psi1, Psi2 are occupied molecular orbital set. This is ground state configuration. So thermal condition, ground state, we pick up the HOMO level. So in this 1,3-beta-diene of pi system, HOMO orbital is Psi2. So Psi2, so how do you present in the diagram? So how many nodes are there? Only one node, Psi2 orbital. So 2 minus 1 one node comes here, one node comes here, between one node comes here. Both the orbitals have same lobes, one side, opposite side. So if you can't rotate, con rotation takes place bonding type, allowed type. For and system, thermally allowed con rotation. So here you can see easily, this is the terminal carbons. Con rotation, like this rotate, terminal rotation. So thick comes between, here thick comes top to horizontal. So both the thicks allowed interaction. So this is the con rotation. So all possible rotations you do. So next disrotation. Disrotation, here not given disrotation. So disrotation I want to explain. That's why if you disrotate the molecule, one is the clockwise direction, one is the clockwise direction, other one is the anti-clockwise direction. If clockwise direct, so this is thick lobe like this, so empty lobe comes like this. So thick and empty opposite lobes, so it is not bonding interaction, it is anti-bonding interaction, not allowed. Boron system photolite thermal disrotation not allowed. Boron system con rotation allowed. At thermal condition. Next one, if you observe photochemical condition, so in photolytic condition, excited state electron configuration need. From this electron configuration, you can select HOMO orbital of pi system. So in this Psi3, 2 nodes is there. Here you can write one node, here also one node come. So both the terminals have same lobes. So disrotate, if you take disrotate opposite, this is clockwise, this is anti-clockwise. So disrotation thermally allowed rotation. So conrotation, this is clockwise, this is clockwise conrotation. So conrotation photochemically not allowed. So here mistake is there, you examine this diagram once again. It is some mistake is there in the material. So thermally allowed pour and system, sorry, total result written here, so pour and system disrotation thermally forbidden. Okay, pour and system disrotation photochemically allowed, you check here conrotation. So conrotation not allowed, anti bonding. Before conrotation at thermal rotation allowed. So here disrotation thermally forbidden. Pour and system disrotation photochemically allowed. So don't confuse. If disrotation allowed, automatically conrotation forbidden. If conrotation allowed, automatically disrotation forbidden. So here conrotation not allowed, forbidden. Automatically disrotation allowed. Pour and system here written. Pour and system photochemically disrotation allowed. So this is the electrocyclic reaction for FMO approach, for electrocyclic reactions. So next one cycloaddition reaction. In this two parts involved, we get only one part or one product. So addition between two unsaturated partners to form a cyclic addition product is known as cycloaddition reaction. So already just now we have discussed in this chapter. Two partners, two conjugated systems or two pi systems involved. That's why cycloaddition reactions by the expense of two pi bonds, two new sigma bonds formed. Again, cycloadditions are two types based on number of pi electrons are participated in addition reaction. So 2 plus cycloaddition, 4 plus 2 plus cycloaddition. So depend on participation of pi electrons. So for both the reactants has 2 pi electrons are involved in addition reactions. This is dimerization of ethylene reaction. Here 2 electrons, here 2 electrons, 2 pi electron system. So total 4 pi electron system, we get to cyclobutane. Here 2 pi bonds consumed in cycloaddition reaction, we get two new sigma bonds we formed in this type reactions. 2 pi bonds lost, 2 new sigma bonds formed in this type reaction. So one more best example, 4 pi plus 2 pi cycloaddition. In addition, 2 pi electron of one reactant, 4 pi electrons of another reactant are involved in, that is Diels-Alder reaction, 4 pi 2 pi system. So in the presence of light or photolytic, we get cyclohexene. So here if you want to FMO approach, so one HOMO orbital, other one is the LUMO orbital you take. If HOMO, select from ground state, or if you predict the thermal condition, both the HOMO LUMO select from ground state only. If you predict photolytic condition, HOMO orbital from ground state, LUMO orbital from excited state. That is the condition, very very important condition. If you predict thermal condition, both frontier molecular orbitals select from ground state only. But in the case of photolytic condition, HOMO select from ground state, LUMO select from excited state. That is important condition. So you can easily check bonding, anti-bonding character, allowed or not allowed character. So this is the cycloaddition reaction. Next one, sigmatropic reaction. So this is also already you know, that is 1,3 shift tautomerism. You can check Sigma bond tropes means migration. So a concerted reaction in which any atom or any group along with its sigma bond migrates from one position to other position within the pi system is known as sigmatropic reaction. These reactions are indicated by ij notation system, which indicates the position of atom group before. So I before, after J, the migration of the in the system. For example, here 1,3 shift, 1,3 hydrogen shift, take an example, and also 1,5 shift or 1,7 shift. We can easily co-rearrangement 3,3 shift, co-rearrangement 3,3 shift. So here X atom or group migrates from one position to third position with sigma bond. So it is also concerted mechanism or single step mechanism. So one X is at one place, it migrated within the system at fifth place, 1,5 shift. Here also 1,5 shift hydrogen. Here 3,3 shift, 3,3 shift co-rearrangement. So it is very important. Co-rearrangement is 3,3 shift in higher education or GATE or CSIR examination. CSIR examination. So here I indicates starting position, J indicates ending position. So for example, X atom I place to J place and migrates. That is sigma tropic shift. Sigma tropic shift. So tautomerism also 1,3 hydrogen shift, that is concerted type of reaction mechanism. So next one, this is the pericyclic reactions classification. First one electrocyclic reaction, second one cycloaddition reactions, third one sigmatropic reaction. Sigmatropic reaction. So electrocyclic reactions, if you want to check FMO approach, so if to predict thermal condition, HOMO select from ground state. To predict photolytic condition, HOMO select from excited state. In the case of cycloaddition reaction, you can check FMO approach. How do you check? You already examined. So both the HOMO-LUMO orbitals select from both the partners. So from ground state only at photolytic condition, at thermal condition. Both frontier molecular orbitals select from ground state only at thermal condition. Frontier molecular orbital select from excited state one partner, other one is the ground state, that is photolytic condition. Photolytic condition. So it is also sigmatropic shift. Sigmatropic shift three types is there: 1,3 shift, 1,5 shift, 1,7 shift. So best example is given hydrogen shift, that is. So COP is the 3,3 rearrangement, COP rearrangement. So you can check this is stereospecificity more present in this type reactions. So pericyclic reactions, single step reactions or concerted type reactions. So thank you one and all.